All right. Hi, my name is Sixin Zhang. I'm very glad to present a recent paper about Nash equilibrium in GANs in an idealized setting. And the motivation is that in GANs, people study different optimization algorithms to find some sort of equilibrium, like Nash equilibrium. And the trouble is we don't fully understand why this equilibrium exists. So in this work, I'm going to give you first a broader view of the topic, and then go into a specific setting to study the richness of this existing problem. So I start from likelihood free density estimation. The goal is here to estimate a probability density P using a P alpha from n realizations of these two densities. And so in the literature, the classical way is to do a maximum likelihood estimation, and that is based on maximizing an empirical mean of the log likelihood function of the model by using n samples from data. And we know that there are many theoretical consistent results, and there are asymptotic optimal rates. And the trouble is, if in certain cases P alpha cannot be evaluated, such as generated by neural networks, and then we need to move on to other ways to estimate optimal approximation of the density P from P alpha. And so this is one motivation using Wasserstein GANs, because in this problem we can try to estimate the Wasserstein wind distance between these two probability distributions by solving a min-max problem. And there are many theoretical works as well to study the consistency of this problem when we replace this space D from Lipschitz functions by neural network discriminators here, and to achieve similar consistency and estimation rates. And from an optimization perspective, there is still a very challenging min-max problem here to solve, which can be understood as a two-player game. So for this two-player game, and the question is, what is a suitable solution for this problem? What is the suitable notion of solution that one can find so that the solution X alpha has a distribution close to the original distribution X? And if we think about this, there are two ways to think of this game. One is called simultaneous game. That means alpha and D, there's a symmetry between them, and one can play. No one plays earlier than the other player. So the natural solution is called Nash equilibrium, which says that there's a solution alpha dot D dot, which is alpha dot is a local minima for Vn for the D dot, and the D dot is a local maximum. It's a global minimum, global maximum. And there's a notion of local Nash equilibrium, which has that local minimum, local maximum similarity. And there is many optimization algorithms developed based on gradients, and they are unstable. These solutions, they are stable points. And then there's a recent work showing that from Famira, showing that Wasserstein GANs may have no Nash equilibrium. And it is actually motivating another way to think of this problem from sequential game perspective by considering Stackelberg equilibrium and alpha dot. Basically, it is a global minima of a dot of this maximization problem D. So by maximizing D, and then we try to find an alpha dot that has the global minima. And this is a non-trivial and bi-level optimization problem. And then there were different extension of this notion of equilibrium in related works. And so facing these problems, when there is this in what's going on in practical GANs, actually, in Wasserstein in GANs, there was some numerical studies about is there any Nash equilibrium in this form of problem by minimizing alpha, beta, alpha, beta, gamma is two parameters that is often used in Wasserstein GANs. So you can think of if beta is some feature extraction from data X, and the gamma is a dot product to project these features into some number, and then try to find max beta gamma, which is to approximate the Wasserstein distance, and then one attempts to find the optimal alpha that minimize this distance. Now, in this kind of practical GANs, one numerical observation is that if one assumes that alpha dot beta dot gamma is a Nash equilibrium, then one can minimize alpha by fixing the other two variables and saying that it should not change too much. Alpha should not change too much from alpha dot numerically. But that's not the case in the recent paper published in ICML. And so this shows that clearly, visually, the solutions generated by alpha, by minimizing this V and alpha along this optimization trajectory, and gives a pretty bad generator. So it's indicates this is not the solution that has been found by usual optimization algorithms of GANs. They don't give, they are not close to Nash equilibrium. What's interesting for this talk is that we can think of this problem from moment matching perspective by marginalizing the gamma, marginalizing this gamma variable, by considering that solving this max gamma constrained by norm 1, and to reduce this problem to two variables. Alpha is the generated parameter, beta is the discriminated parameter, so the features we want to learn, and to think about this as a moment matching problem. And if we do the same experiment as before from a similar setting, then the SGD we can minimize alpha by fixing beta dot found by existing optimization algorithms. And then what we can find is that the solution doesn't change that much. So it suggests that if we take a moment matching perspective of Wasserstein GANs, actually this solution alpha dot beta dot could be considered as a good Nash equilibrium. And so this is somehow the motivation I want to talk today is to study the existence of meaningful Nash equilibrium in moment matching GANs for a particular case called Gaussian stationary process. And we're going to consider this min-max problem with two variables alpha beta by matching this moment. And the idea is to fix the generator of X alpha and then study the choice of F beta. So that's somehow simplify the study of theoretical study of this whole domain. And we are going to consider a realizable setting that X alpha is a station Gaussian process. So I will tell you what it is. And what's interesting is that in this realizable setting, we can introduce a notion of consistent Nash equilibrium, as in the classical maximum likelihood estimation, that the solution is consistent Nash equilibrium if this one alpha m dot beta dot is Nash equilibrium, and moreover, this as the data sample size increases, the distribution converges to the right one. And I will also show some empirical numerical results about gradient descent methods and towards consistent Nash and non-Nash equilibrium in different perspectives. So Gaussian stationary process is not that far away from Gaussian distribution, but we are interested in that because it has an invariant translation invariance in this process, and we'll see that it has an important role that we can define different features to to, estimate optimal alpha. So this is a convolution between a filter alpha and a white noise Z in some finite dimensional sphere setting. And the realizable setting means that X, the true ground truth process, is generated by another parameter alpha bar and convolved with another white independent noise Z bar. And the question is, can we estimate alpha bar from n realizations of X and X alpha? And this question actually doesn't make too much sense in the Gaussian setting, because what we care is the probability distribution of X alpha close to the X. So what we really want to measure is the covariance matrix. In the Gaussian case, the covariance matrix captures the distribution because we assume the mean is 0. And so this is measured by this covariance matrix error is measured by the Fourier transformation of this filter alpha in the spectral domain by taking the maximum of all the frequencies. And so this can be sort of the eigenvalues of this covariance matrix. And what we are measuring is the maximum difference of eigenvalues between these covariance matrices. And these results are classical. So the main finding of this work is to show that there are across different discriminators. Sometimes we can show there's no existence of Nash equivalent. And we can also construct some consistent non-Nash equivalent solution in some case. And finally, there's an interesting convolutional case that we can establish existence as a uniqueness of consistent Nash equivalent. The uniqueness means, because we are not in a convex concave band problem, the uniqueness means that for each equilibrium, we are trying to say that it is a consistent Nash equivalent, and in this sense, it is unique. So let me go a bit more into these notions of equivalent Nash equivalent than the consistency. So for this problem, we assume that Vn is differentiable, and we try to define the equilibrium on the classical way that we assume there is no boundary, and then the gradient is 0. So that's the stationary point usually in optimization. So that's the equilibrium. And Nash equivalent is saying that locally or globally here, you don't want to move if you don't change another player's strategy. And then if alpha beta open set, then we know that Nash equivalent is occurring because that's the first order critical point condition. And in the trivial case is when there are infinite number of data n equals infinity, then Nash equivalent of n always exists. And that's the original GAN paper showing that, okay, that's why everybody seems to look for this notion. But the non-trivial case is when n is finite. And here, that's what I want to study. And if we have finite data, then we can define a finite sequence alpha n dot beta n dot, which tends to this, like, let's say we have a consistent generator. That means the covariance matrix they tends to 0 in this particular Gaussian stationary process case. And this is nice because one can construct explicitly a consistent generator set alpha n here from the Fourier analysis. And so this basically says that we can match the eigenvalues empirically of this from using the n finite samples of data and well. So this is classical. So we can define that, and then once we have this consistent equilibrium, this basically says it is equilibrium, then alpha n is consistent. And we can extend that to consider the Nash equilibrium, saying that alpha and beta n dot, it is almost surely the technical it is needed later on. So it's the Nash equilibrium, and the alpha n dot is a consistent generator. So this is basically combining the classical notion with this consistency. And interesting, we can also define a consistent non-Nash equilibrium notion, and because in practice, sometimes people observe a non-Nash equilibrium and by looking at the Haitian structures of the GAN. So I will detail this later on. And basically, this shows that the existing method tends to converge to non-Nash equilibrium. And so why it still works. So, and one interesting, I think, insight from this work is to say that consistent non-Nash equilibrium can exist, and it works because it is consistent, but even though it is non-Nash equilibrium. So here, this is a bit more subtle to define what is non-Nash equilibrium. It is equilibrium, but it is not Nash, and the rest is the same. So let me just don't go into too much details about this. And just by showing you the three cases that I have talked about. So the first one is the real discriminator. By considering is there any Nash equilibrium in this GAN Vn? By looking at this two sides, this is alpha generator, and the beta is the discriminator. It is simply a real valued vector with a unit norm constraint. So we are trying to project data up to some direction and looking at the modulus group. And the theorem is under some technical assumption that the number of data is larger than 2, the dimensionality of X is even, and the alpha bar, that's the ground truth generator parameter, is not degenerate. That means there's no zero eigenvalue in the covariance matrix of X. Then under this assumption, we can show that there's almost surely no Nash equilibrium in this game. And I will say that this extends the existing results to which was studied in unrealizable infinite data setting to a realizable finite data setting. We can draw an analogy because in finite sample setting, a realizable problem becomes somehow unrealizable. So that's why we can expect to obtain similar results. Now, the principal issue for this unrealizability due to finite samples is essentially due to the fact that we cannot find an alpha that matches perfectly the covariance matrix of the empirical covariance matrix of data X. And this needs to be why we need some technical assumptions to show this. But I think in general it is true. And the proof sketch is to say that assume that alpha dot beta dot is a Nash equilibrium, then we can argue that beta dot should be a global maximum of this Vn, and then alpha dot is the global minimum. Then what we are going to do is to show that the global maximum, the value of the maximum value of the Vn for beta is non-zero. This is measuring actually the covariance matrix error squared, and this error is non-zero, but we can still find alpha that has achieved a smaller value that is 0. So this is the key idea to construct actually an alpha that equals for the Vn alpha, but for any beta dot, we can construct alpha that this equals 0, but the maximum solution, the Nash equilibrium solution, is non-zero because the covariance matrix cannot be matched. So this is well, this I will skip this because this essentially solve a quadratic problem by looking at the some eigenvalue of the covariance of some symmetric matrix. So for the second case, we can think of So this is motivated by some Fourier basis analysis, because we know that the Fourier basis diagonalized covariance matrix of jointly diagonalized for all the alpha. So this is constructed by projecting X into some basis with indexed by L. So we have m directions, and if we choose m equals d, then we can expect to get a basis, and this is somehow reduced discriminant is somehow trying to capture covariance eigenvalues, this information, and then we can expect that this minimization problem would not create would be stable, doesn't change much the alpha, which was not the case in the real discriminator case. So that's why we use multiple features m equals d by constructing explicitly a Fourier basis solution. And then we can show that for all alpha dot in the consistent generator set. I will remind you that this thing is constructed by M. And in this set, we can show that this solution is consistent, equivalent. And moreover, under our assumption 1 that we used before, which is technical, so this thing is a consistent non-Nash equivalent. So it is consistent. So that means it works in practice, but it's not a Nash equivalent. So the proof sketch is based on the similar idea of moment matching. But here we can achieve a perfect moment matching because we only measure the diagonal terms of covariance matrices. And then we need to compute to show that it is non-Nash by looking at the Jacobian matrix. These are the matrices people usually to compute in practice and to see whether it is a Nash equivalent or not. So the necessary condition for Nash equivalent is that the diagonal terms, these two diagonal blocks, this one and the beta, they should be semi-definite positive. And it is the case that this is obviously true in our setting, but this is not the case actually. And so that's why this creates some instability along beta rather than alpha. So there's some issue when we can still improve beta actually in this case. That's why it is non-Nash. So let me skip this. Basically, we are trying to show that this relation of the Vn beta has at least one positive eigenvalue. And it is true because the covariance matrix has to be zero if you don't want any contradiction. But this cannot be the case as we have seen before. What's surprising is that this covariance matrix, the error tends to be very small and the number of data goes to infinity. And that means the solution, although it is not Nash equivalent, but it tends to be a Nash equivalent as the number of data samples. So that's why probably in practice, people don't observe this instability if the data sample size is large. Now let me move on to the last the last case, that is the convolutional discriminator. We want to study its existence and uniqueness. So we are trying to convolve data with different features, and by taking the modular squared. Note that this norm squared, so these are measuring actually invariant features of the eigenvalues of these covariance matrices. And what we can show that the existence is quite simple. If alpha dot is in the consistent generator set, beta dots are NA, arbitrary actually, then it is a consistent Nash equivalent. Because in this setting, we still have the perfect moment matching. That means the Vn alpha dot beta dot equals 0. And one cannot do that. Now, what's more interesting is about uniqueness. That means if we have equilibrium, if it is equivalent when this is a consistent Nash equivalent. So these are the sufficient conditions that I find here, which are relevant, is that the last two, and they basically saying that beta dot should not be degenerate. It should be somehow generate some basis, and then it can allow us to infer that alpha dot is consistent in consistent set. So this is motivates us to study this open set of the subset of beta, which is here, to satisfy these two conditions. And this set, under this uniqueness result, we can say that this the n equivalent of this subGAN with this subset beta 0 is consistent measure. So this is the uniqueness. And so this motivates to study whether in practice those gradient descent method algorithms always respect this, always stays in this, if it starts from beta 0, whether it stays in beta 0 or not. And we will see that numerically what happens. So I will briefly show these two numerical results. One is the discrete time GDA, and so one is alpha is trying to minimize Vn during gradient descent. The other beta is during gradient ascent. And we can also consider continuous time GDA because it's usually more stable. And we're going to study global convergence of continuous GDA in the convolutional discriminator case. And also here the local convergence of discrete GDA in the complex discriminator case. So here is the first result about global convergence. And we'll start from random initialization. And by changing different number of data samples, we can observe different 10 simulations of these trajectories. And we'll see that pretty well when the loss on the n t goes pretty small. And the question is, do we achieve some sort of global convergence to the consistent Nash equivalent or not, if n is big, for example? So for n is big, here we can measure closeness of alpha t to the consistent set alpha n by looking at this quantity, this error. If this error is 0, then we are in this set. And we can track this numerically and see that it's indeed pretty small. And we can also ask whether beta t stays in beta 0, because if we are always inside this beta 0, then as long as when converged to equivalent, then we are sure that it is a consistent Nash equivalent. So this is a confirmation of this situation that these two quantities actually converge to something non-zero. That means we are in this set. Now, for the local stability, the complex at beta, complex discriminator, we can still expect that gradient descent algorithm may be stable near non-Nash equivalent, because actually it can happen. It can happen, but it depends on the Gaussian structure. So we can measure this two distance. One is to the consistent set. The other is the distance of beta in the Fourier basis. And here is one result for the discrete time GDA. We can see that if n is small, then this dynamic is not stable. These things we expect that it stays close to 0, but sometimes it just blows up. So that's not stable. But if n increases, then we becomes pretty stabilized. So we can still run this much longer for 10 to the 100 times longer. Then we still can observe sometimes, even in n is big, these solutions can diverge, start to slowly diverge. And but we can. So that's why it's nearly stable. But one interesting observation is that the error of the covariance matrix error doesn't change much along these trajectories. That means the quality of the generator, even near this non-Nash equivalent, it stays pretty stable in this sense, and for discrete time in GDA. Okay, so let me conclude. So this work studies the equivalent structures of GANs in realizable finite sample settings through moment matching and the sequential GAN perspective. And Main finding is that a suitable discrete family can result in the existence of consistent Nash and non-Nash equilibrium. And we can also show that it can be nearly stable, this non-Nash equilibrium, when the number of data samples goes to infinity. Well, I have to admit that to extend these results to other GANs remains very challenging, because one needs to identify a consistent set of consistent generators alpha n, as we have used before, and then to show that one can achieve perfect moment matching. But this is probably very rare in finite data sample case. And then we still want to analyze the local stability and global convergence. So I think there are still many things to be done. And what's interesting puzzle for me is there any like moment matching this perspective? One can argue sequential gain maybe is not a good perspective, or it's more natural to think about it. It should be it should be a two-player like sequential, or excuse me, or it should use a simultaneous gain perspective, not a sequential. So this may be one way is not natural than the other one. Is moment matching a natural perspective or not to model high-dimensional data such as images? I think the results we have found in our MNIST is interesting to think forward, because it shows that there's some moment matching effect, because it seems to we have the Gaussian GAN has found like a pretty stable solution from this perspective, but it is not a stable solution from the Gaussian GAN perspective. Anyway, so let me stop here. I'm glad to answer any questions.
Thank you, Sixin. So it's time now for